A novel ice-breaking technique conquers the Arctic. An unusual hull shape significantly improves the economy of shipping in ice-covered waters, reducing fuel costs by 65% during ice shipping. An increase in operating range in ice of roughly 185%. How is this possible? A conventionally built ice-breaking ship breaks the ice cover by crushing and bending it in a rocking motion, accidentally falling with her wedge-shaped bow through the ice cover where it gives way, and trying to push the broken floes to the side to where the ice cover is still unbroken. In these shots filmed underwater, we can see how the ice floes travel under the ship's bottom and are finally broken up by the propellers, thus endangering propellers and machinery by ice impacts and impairing the efficiency of the propulsion system. The novel German development works on a quite different principle. The Thyssen-Waas icebreaker breaks the ice cover in a controlled ice-cutting process with a very smooth ship's motion, which considerably increases the living comfort on board. The ice floes are removed from the propeller intake, producing a clean-cut, virtually ice-free channel behind the ship. How does it work? During forward motion, the novel shape of the ship, with its widest portion at the front of the sloping, flat bows side edges, cuts a wide ice panel out of the solid ice cover, taking advantage of the low shear strength of ice, until the panel breaks off across the full beam of the ship by cantilever bending. The large, almost rectangular floe travelling down the bow is split at the centre runner, and the two halves of the split floe float up hydrodynamically under the unbroken cover at the ship's sides. The basic principle is demonstrated in the following animated sequence. Here we have an isometric presentation of a Thyssen-Waas shape. The main characteristics of the bow are the flat bottom and the sharp cutting edges parallel to the midship plane. The cutting edges are wider than the underwater ship behind and above them. Thus, a channel wider than the ship's main body is created, reducing friction at the ship's sides. The edges of the bow are accentuated by sharp runners. The flat bottom tapers into a V-shaped part of the foreship, and this fares into the ship's main body. The flat bow, the greater width of the bow, the sharp side runners, and the V-shaped part behind the bow are the main characteristics of the Thyssen-Waas concept. The actual ice-breaking process occurs in 3 phases. In the first phase, the sloping bow slides onto the edge of the ice. The weight of the ship exerts a vertical force along the runners of the bow, creating two sheer cracks in the ice. In the second phase, the wide band of ice cut out by the cutting edges is bent downwards by the onward moving bow, and finally fails in the cantilever mode across the full beam of the ship. The large floe, the full width of the ship, is further submerged and split by the bow as it proceeds. In the third phase, the almost rectangular halves of the large floe are transversely displaced by hydrodynamic and buoyancy forces due to the specific shape of the ship, and come to rest under the unbroken ice cover at the sides of the ship. In this way, an almost ice-free channel is created. And here's the proof. This ship, the modern Soviet icebreaker Modyug, built in the conventional way in 1982 at a Finnish yard, was converted into a Thyssen-Waas ship in 1986 in Emden, West Germany, with excellent results. The white area shows the extent of the conversion. This is the Modyug story. Arrival in Emden at the Thyssen-Nordseewerke. This shipyard is well known for its novel developments. The Soviet crew look on with great interest. A new foreship had already been built prior to the arrival of the old ship. Docking the old ship. Immediately after its arrival, men got to work with their torches. The old forebody is slipped ashore. The new forebody is slipped into the dock. Precision work. Extensive model testing in the HSVA ice tank in Hamburg was carried out. The new bow in a ridge test. The old bow in a ridge test. The new shape offers improved opportunities for freeing trapped ships. Very close passage distances are possible. The trapped vessel is now free. The ship's captain, Kozhunyayev, was cautious when answering questions. At the moment, I don't want to make any definite predictions. Let's talk again after the full-scale trials.
Чувствуется по настрою и по той ответственности, с которой подходит верфь к этому вопросу, все будет благополучно.
However, in view of the professional approach of the yard, I have the feeling that things are going to turn out successfully. Leaving for the full-scale trials. Out in the North Sea. It can be clearly seen how air is trapped and collected under the bow, thus dampening slamming peaks. Approaching the Lofots, sailing against a Beaufort 8 to 9 storm. Arrival in the Spitzbergen test area. The physical data of the ice to be broken is subjected to scientific investigations. Ice-breaking tests at 135 centimetre level ice at 7 megawatt propellers power. Speed 3 knots without any hull lubrication. With a water curtain in operation, the picture changes. Speed increased to 3.3 knots. With Jastram air-water jets, a further improvement. Speed increase to 4 knots. Excellent maneuvering capabilities. clean-cut turning circles. And 180-degree turns with minimum space requirements. Herringbone star manoeuvre. A unique novelty, the ship can precisely widen her own channel at any desired distance parallel to the old course, with her centerline exactly on the old track's edge. Or with her full beam over the old channel's width. The pack ice in the northern Barents Sea had formed huge ice barriers, ridges, which were to be measured and broken. The test crews in the ridges need protection from the polar bears wandering around. HSVA's sonar equipment is lowered through a borehole in the ice to measure the underwater profile of the ice ridge. An enormous mass of ice up to 13 metres below and 3 metres above water over about a 300-metre path shows up on the monitor. How is the Thyssen-Waas ship better able to break ridges than a conventional ship? A V-shaped bow crushes and bends the ridge against the high crushing and bending strength of the ice, wasting a lot of impact energy in generating horizontal compression forces in the ridge. The Thyssen-Waas bow, however, uses all its impact energy to shear the ridge and to push the broken part downwards where the water gives way. Some refreshment after a day on the ice exploring the dimensions of a mammoth ridge. First attack on the 300-metre Mammoth Ridge. The ship comes to a gentle stop. And reverses. After a few runs, the giant ridge is cracked. The ship heading for her duties in the Soviet polar seas. Sailing in pack ice on the Barents Sea. The life rafts on deck give an idea of the size of the ice blocks. workhorse Mudjug in the White Sea. Here she's freeing her unconverted sister ship Dixon, which is trapped between huge ice barriers. Freeing other trapped convoy ships. The ships are then towed to safety. What's the message of the Mudjug? That the Thyssen-Waas technique has proved itself and offers great promise. Changing the shape of the hull has had dramatic results. A drastic reduction in fuel consumption by some 65%. An almost 100% speed gain in ice at MCR, or still considerable speed where the old ship couldn't move at all. A dramatic increase in operating range in ice by about 185%. The final results are documented in full power curves showing at which speeds the ship can break which ice thickness. On the left for the old shape, on the right for the converted ship. The marked increase in breakable ice thickness is obvious. Over the seasons of the year, ice thickness grows from 0 to a maximum at spring breakup, which is marked by a sudden disintegration and melting process. The length of the shipping season is dependent on the ice thickness the ship can break. The new Mudjug offers the possibility to extend the length of the shipping season by at least 80%. Smooth, comfortable and low-cost sailing in ice is a reasonable expectation for future polar shipping. A promising new technology. Thyssen-Waas ships. A revolution in ice shipping.